Hello and welcome to CMA 8th Grade Math Academy. I'm your teacher, Mr. Schrog, and today I'll be teaching you about sequence formulas. We'll need pages M1 136 through 144. But before we get into the sequences, I thought I'd start off with a little hilarity. So here's a joke for you. How does the man on the moon cut his hair? Eclipse it. Ha 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 ha. Oh, that's a good one. All right, well, back to business. Down to our learning goals. What will we be learning today? Students will be able to create an explicit and recursive formula for both geometric and arithmetic sequences. We learned about geometric and arithmetic sequences yesterday, about the difference in those. Today we're going to be writing formulas for each. Why do we want to do this? Well, frankly, these are going to help us save a lot of time. You will not have to write out every single term in order to find the 100th term in a sequence. Yesterday, we had to write out all the terms. But today, we're going to be able to just save time and say, hey, if I want the 100th term, here's my formula, plug some stuff in, boom, we're done. Okay? And how will you know when you've been successful? When you're given a sequence, you will be able to create a formula to determine any number of terms in the sequence. All right, so let's get started. On page M1 136, there is a scenario. Then there is a table and some questions that go along with it. I think as is, you have enough information, you know enough about formulas that you can complete this page on your own. So what I want you to do is read the scenario, complete the table, answer the questions. You've got 5 minutes to do that. After 5 minutes, I'm going to come back on and we're going to check our answers, and then we will move on to writing the formulas. All right, you've got 5 minutes. Ready, go. Alright, your 5 minutes is up. So hopefully your table that you filled in looks something like this. We know that the first term would be if he hit 0 home runs, and then the amount of the donation is going to be $125, and then it's just going to go up by $18 each term because each home run is worth $18. So we know it's just going up. We're adding 18 each time, so it's an arithmetic sequence. We know the common difference is 18, and that just means we're adding 18 each time. So if we were trying to find the 10th term, that should say 10th term, not 19th term, we would add 18 to the 19th term to do so. Okay? Page M1 137 is where we're going to get into writing the formulas. The first couple formulas that we're going to learn are going to be for arithmetic sequences, which just means they have a common difference. We're either adding or subtracting the same number over and over and over and over, and that's how the pattern is formed. The first type of formula we're going to write is called a recursive formula. Everybody say recursive formula. Good. Now, a recursive formula basically just tells us the new term based on the term right before it. Okay, so this is really what a lot of you were using yesterday when you were figuring out the next 3 terms in a sequence, because you were looking at the previous term and you were either adding or subtracting something to get the next term. Okay? So you were really doing a recursive formula in your head. We just didn't have it out formally like we do here. So if you take a look right here in the middle of the page, we have this formula that's written out, and right now it kind of looks kind of hard to understand. Okay, so the first term, which is a to the n, just means the nth term, which means whatever term we're after. So if we're looking for the 12th term, this would be A12. The A just stands for arithmetic, because that's the type of sequence, and the 12 just represents the term number. And then that would be equal to A, again, the big A just means arithmetic sequence, to the n minus 1. So, well, if n is 12, n minus 1 would be 11, so then we would be saying the 11th term, plus the common difference. Okay? So again, that's what you were doing yesterday. If you were trying to find the 4th term, you looked at the 3rd term, and you either added or subtracted to it to get the 4th term. Okay? But now we just have a more formal way of looking at it. At the bottom of that page, then it says, use a recursive formula to determine the 11th term in the sequence. Explain what that value means in terms of this problem situation. Well, I don't really have room right there to write, so I'm just going to do it up above, but you can write this next to number 1 on your page. Okay? So we know we're looking for the 11th term. So the first part of this formula just is A11 for the 11th term. And we know that it is A n minus 1, so 11 minus 1 plus the common difference. Okay? Now what we're going to do is go through and put in the actual numbers for each part of the formula. So a to the A11 stays the same. We're still looking for the 11th term. A to the 11 minus 1 becomes A to the 10th term, A10, plus the common difference in this case, it was 18, because for every home run that's hit, he donates $18. Okay? Now the only thing left to put in is what A10 was. Well, the 10th term was actually 9 home runs hit, and we did it on the previous page in the table, and it was 287. So really what we have is A11, which means the 11th term, is 287 plus 18. And then we just do 287 plus 18, and we get the 11th term is equal to 305. Okay? And in terms of the problem, that means that there's going to be a $305 donation. And it also means that there were 10 home runs hit. Even though it's the 11th term and you would think, oh, well, there were 11 home runs hit. That's not true because term 1 was 0 home runs. So the number of home runs is always one less than the term number. So remember that as we're going through these formulas. Okay? Question 2 says, is there a way to calculate the 20th term without calculating the 19th term? If so, describe the strategy. Okay? Well, we haven't learned anything like that yet, but that's leading us into the next page. So if you turn to the next page, which is page 138. We're going to be on 138 and 139. We are now looking at what's called an explicit formula. So now everybody say explicit formula. Now this formula I think is more helpful because as it says here, it helps you calculate the nth term of a sequence using the term's position in the sequence, which just means we don't have to know the previous term anymore. We can just say, hey, I want to know the 20th term. As long as we know this formula, we can plug in 20 for n, and we're good to go, and it will give us really quick, easy answers. Okay. So if you look here, it says an, again, this is the same thing. It's arithmetic, and it's the nth number term, whatever term we're after, is equal to, here's where it gets different. It's a1. It's not a to the n minus 1. It's just a1, which means the first term in the sequence. Plus the difference, that's the same, except now the difference is getting multiplied by n minus 1. Now this is not the n minus 1 term. This is literally whatever term we're after, whatever number that is, minus 1 times the difference. Okay? So let's see what this would look like when we put it into action. So again, we're going to do on, I guess this is on page 139, we're going to use the explicit formula this time to find how much it will cost for 35 home runs. Now, remember, 35 home runs really means the 36th term, because if you recall, the first term is 0 home runs. So 35 home runs is really the 36th term. So we're really trying to find the 36th term. So we're really trying to find a to the 36th. And that's going to be equal to a1. Well, the first term in the sequence was 150 plus the difference is 18. And then here's where I said it's literally in the number term minus 1. So we're not putting in the 35th term, we're putting in 35 because that is 36 minus 1. And when we do the math and we find all this out, we find that the 36th term is equal to 755. So in this case, he will contribute $755. Now let's do the same thing with 48. Again, it's not the 48th term we're after. We're actually after the 49th term. So a to the 49th is equal to, it's the same first term, which is 150. It's the same difference, which is 18. But in this case, it's 49 minus 1, which is 48. And when we go ahead and do the math, the 49th term is equal to $989. Just under $1,000. All right, now what I want you to do for C and D is to plug in 86 and 214 into the explicit formula. But remember, 86 home runs means the 87th term. And 214 home runs means the 215th term. So plug those into the formula and see what you get. I'll give you 2 minutes to do that. Ready, go. And when you are finished, you can look up here and check. So the 47th term, which would mean, or sorry, 87th term, which would be 86 home runs, is 1,673. And the 215th term, which would be the same as 214 home runs, would be 3,977. All right, good. So now you have successfully written an explicit formula for an arithmetic sequence. So, what you're going to do now that you've had some practice is you're going to write the first 5 terms in a new sequence based on the new information, which says that Rico decides he's going to now start with a contribution of $500 and donate $75 for every home run. So he's going to donate a lot more money. So you need to first do the first 5 sequences, or terms in the sequence, and then write a formula to find the 39th home runs and the 50th home runs. Well, you're going to want to write an explicit formula because you don't want to have to put out 50 terms to get that 50 home runs. So, right after you do the 5 terms, you're going to write an explicit formula and use that for A and B on number 5. Okay? That gives you about a minute for each question. I'm going to give you 3 minutes, and your time starts now. So, now that your time is up, we are going to check our answers. So, question number 4 was write the first 5 terms in the sequence. So, based on the new information, he started with 500. That's if he hit 0 home runs. And then he's adding 75, so 575, 650, 725, and our last term would be 800. There's your first 5. Now, to find the 39 home runs and the 50 home runs, it would be the easiest to write a explicit formula. So the explicit formula we know is a to the n, which just means the nth power of an arithmetic sequence, should be a1, which is the first term, plus the common difference times n minus 1. Now what we need to do is fill in some of these parts. A to the n stays the same. Our first term is 500 in this case. And now our common difference is 75. And the n minus 1 also stays the same. Now with this formula, we can find 39 home runs or 50 home runs with relative ease. Just remember, when you're plugging in 39 home runs, it's really the 40th term, and 50 home runs is really the 51st term. When you plug those in, so when you have a to the 40th term, a40, you get 3,425. And when you plug in the 51st term to find 50 home runs, you get 4,250. So there you've done it. You successfully created 2 explicit arithmetic sequences, and then you use them to find random term numbers. So that leaves us with geometric sequences. So we're going to kind of do the same thing here. On page 140, it's another formula. This time it's geometric sequence. You're going to go through, you're going to fill in the table, you're going to answer the questions, then we're going to come back up here and check, just like we did with the arithmetic sequences, and then we're going to learn how to write a recursive and explicit formula for geometric sequences. But first, you need to complete page 140 by reading the scenario, filling in the table, and answering the questions. This time, since you kind of already know what you're doing, I'm just giving you 4 minutes. You're going to have to use your time to work quickly, all right? Your 4 minutes starts now. All right, your 4 minutes is up. Hopefully you were able to fill in that table and get those answered. So we can tell right away that this is a geometric sequence, and you are multiplying by 2. That's the common ratio, is 2. Term number 1 is 1 cell, and that 1 cell splits into 2, and then 2 becomes 4, and 8, and 16. We're doubling each time, multiplying by 2. So if we wanted to find the 10th term, we would find the 9th term, and then we would multiply it by 2. But that's not a recursive formula exactly, but we kind of did that in our head. But now we can write a recursive formula. So that is the next page, page 141. We are going to actually write a recursive formula for a geometric sequence. Okay. Again, it's very similar to the arithmetic one. The difference here is we've got Gn, that's the same. It's a G instead of an A, but it's just whatever term we're after. And that is equal to the previous term, right? G to the n minus 1 just means whatever term we're after minus 1, the previous term, times the ratio. Instead of adding by the common difference, we're multiplying by the common ratio. Okay? So we are after the 12th term in the sequence. Okay? Well, we know that we have to write it as G to the 12th, and that is going to be equal to G to the 12th minus 1 times the common ratio. And we just need to plug in what we know. Well, we know that the previous term, the term 11, is 1024. We're still after G12. So G11 is 1024, and we know that the common ratio is 2. We're multiplying by 2. So now that we know that the 11th term is 1024, we just multiply by 2, and we find that the 12th term in this geometric sequence is equal to 2048. Okay. And what does that mean in terms of the problem? That means that that's how many cells there will be after 11 divisions. Now, the reason I say there's 11 divisions in the cell is because term 1 was 0 divisions. There hadn't been a division yet. Okay? So this is after 11 divisions is the 12th term. Okay? Similar to the home runs, our first term was 0 home runs. Here, it was 0 divisions in our first term. All right. So now, we're going to learn how to do the explicit formula for a geometric sequence. Okay? So we have, again, it starts out the same way that all of these have. starts out with g to the nth term, which just means whatever term we're after in a geometric sequence. Just like the arithmetic one, it starts out equal to the first term. So whatever the first term in our sequence is goes here, and that is getting multiplied by r. Instead of r being multiplied by n minus 1, now it's to the n minus 1 power. Okay? And again, that's just a number, not the actual previous term. So if we're after the 100th term, this would be 100 minus 1, so it would be to the 99th power right here. Okay? So we're going to write a formula for this geometric formula. We're going to write an explicit formula, and then we're going to use it to find 11, 14, 18, and 22 divisions. Okay? So we know that it's going to be g to the n because that's just our nth term. And we know that the first term in our sequence is a 1. We know that each time it's getting multiplied by 2, so our common difference is, or our common ratio, sorry, is 2, and then that'll be to the n minus 1 power. So if we want the 11th division, that's really the 12th term. So g to the 12th term is 1 times 2 to the 12 minus 1, which is the 11th power. Well, 2 to the 11th power is 2048 times 1 is 2048. So we know that g to the 12th is 1048, which we already knew from the recursive formula, but this just proves that it comes out the same when you have the explicit formula. Then when we go to 14 divisions, 14 really means g to the 15th term. We want the 15th term, not 14, because 14 divisions means 15th term, which means that we're after the first term still 1 times 2 to the 15 minus 1, which is 14. And when we take 2 to the 14th power, we get 16,384, and we take that times 1, and it's still 16,384. So that is for B. 14 divisions would be 16,384. Now what I want you to do is find for 18 divisions and 22 divisions. But remember, 18 is the 19th term and 22 divisions is the 23rd term. All right, I'm going to give you just a couple minutes. Ready, go. All right, so you should have gotten for 18 divisions, which is the 19th term, 262,144. And the 23rd term, which would be 22 divisions, is 4,194,304. Now, moving on to the next page, which is 143, we are supposed to suppose that now there's 5 cells starting out in the Petri dish, and the growth pattern is going to change. Now it's going to be divided into 3 daughter cells each term. We're supposed to write the first 5 terms in the sequence, and then determine the number of cells after different divisions here at the bottom. So, for question number 4, we need to write the first 5 terms in the sequence. Well, it tells us that they're starting out with 5 cells in the Petri dish. So we know it has to start with 5. That has to be our first term. Then each time it's getting divided into 3. Well, 5 divided by 3, we're not dividing by 3 because they're actually getting split up. So it's really like multiplication by 3 because they're getting more and more. So now we have 5 times 3, which is 15. 15 times 3, which is 45. 45 divided times 3, which is 135. That's 4 terms, and then our 5th term would be 405. So there's our first 5 terms, 1, 2, 3, 4, 5. Now, to determine the 13 divisions and the 16 divisions, I like to have the explicit formula. That's the easy one. So, let's write an explicit formula here. We know it's going to be g to the n term. We know it has to be g1, the first term in the sequence. And then it's times r to the n minus 1. Okay. Well, we know the first term is 5. We know that our change, our common ratio is 3, so let's fill those in. So we know that this is really 5 times 3 to the n minus 1. So then when we move down here, for 13 divisions really means the 14th term. So we are looking for G14. The 14th term is going to be 5 because it's our first term times 3 because it's our common ratio, and then 14 minus 1, which means 13 divisions to the 13th power. And when we solve this, we get a really big number. We get 7,971,615. Okay. Then when we plug in the same thing for 16 divisions, except now it's the 17th term, and we plug in 16 where it's n minus 1. I'm running out of space to write, so I'm just going to write the answer. So we should get 215,233,605 when we plug that in. Alright, so now you have successfully written 2 explicit formulas for geometric sequences, 2 explicit formulas for arithmetic sequences, and a recursive formula for both. We need to put this to use and practice our new skill. So, what we're going to do... Oh, I'm getting ahead of myself. First, we're going to do the talk on page 144. So on page 144, it says, explain the advantages and disadvantages of the recursive formula, and explain the advantages and disadvantages of the explicit formula. Okay? I'm going to give you 2 minutes to write, and then you're going to share with your group. But right now, you're just silent, writing on your paper. This is page 144. You've got 2 minutes. Ready, go. All right, your 2 minutes is up. So we're going to talk in our group. We're going to start with person number 1. Person number 1 is going to explain the advantages and disadvantages of the recursive formula. You're going to give your answer. Then person number 2 is going to paraphrase what person number 1 said. Then person number 3 is going to give their answer for number 2. And person number 4 is going to paraphrase what they said, what person number 3 said about the explicit formula. Okay? So 1s and 3s, you're giving your answer. 2s and 4s, you are paraphrasing or summarizing what somebody else said. Okay? Ready, go. All right, I heard some good discussion with that. We are going to go ahead and go on to what I was trying to get us to go to earlier when I was ahead of myself. Okay? In the previous chapter, we cut out some different formulas. Okay? And we found the missing terms in the sequences, and we wrote down what was happening and if they were geometric or arithmetic. And so we are going to use those, and we're going to use pages 121 through 132 to kind of sort these, organize these, and then write formulas for them. So if you didn't already, there are also some graphs, I believe, on the pages right after those sequences that we cut out. You're going to have to cut those out as well if you haven't yet. And you're going to match the graph with the sequence. Then you're going to paste or draw. I don't care if you paste them in here or if you just want to draw them yourselves. The sequence and the graphs. And then we're going to write formulas for each sequence. Okay? Then we're going to use the recursive formula to show how to find the 5th term. And we're going to use the explicit formula to show how to find the 18th term. Okay? So I'm going to demonstrate one of each so that you know exactly what to do on the rest of those pages. Okay? All right, so here are my 2 examples that I'm going to go through. We've got on the left an arithmetic sequence, and on the right we have a geometric sequence. Okay? I'll get to the geometric in a second. We're going to start with the arithmetic. Okay? I chose K. K was an arithmetic sequence because we were just going down by 1.5 each time. That was the sequence. We were subtracting by 1.5. So I matched graph 7 because it looked like it was starting right about 6.5 and it was going down at a constant rate each time, going down by about 1.5 to where I got to into the negatives with my last 2 terms, which I know the last 2 terms that I wrote in there were negative terms. Okay? So that's how you would match the sequence in the graph. But what I want to focus on is writing the formulas. So then down in the bottom left is a spot that says recursive formula. Okay? So we know this is an arithmetic sequence, so we know that the recursive formula should have an a, and it should be a to the nth term is equal to, we know it, we need to note the previous term. We note the previous term by saying a to the n minus 1 a to the n minus 1, and then we need to add the difference at the end. Okay, so there is our recursive formula. Now remember I said we were going to find the 5th term in all these. Okay, well the 5th term would just mean a to the 5th, a5, which means the 5th term, which is going to be a to the 5th minus 1, which is 4. So a4, the 4th term, plus the difference, which we know the difference here is negative 1.5. Well, the 4th term was 2, so a5 is 2 plus a negative 1.5. which gives us the fifth term to be a half, which you would already have yours filled in and you would know that it's a half, but the recursive formula would prove it. Then you're going to go over to the explicit formula. You're going to write the explicit formula and also solve for the 18th term. So here we know the formula is a to the n again. Then it's the first term plus the difference times n minus 1. Okay. Well, then if we're trying to find the 18th term, we know that it's a to the 18th. The first term in this sequence is 6 and a half. So we have 6 and a half plus the difference was a negative 1 and a half. And we're trying to find the 18th minus 1, which is really 17. And when you do all the math, you get negative 19. So that tells us that the 18th term in this sequence would be negative 19. And I didn't have to go through and find the first 17 to find the 18th term. I just plugged 18 in to our explicit formula. Okay? So there's an example of how you would do it with the arithmetic sequence. Now when we come over to the geometric sequence, it's going to work very similarly. Now over here, I chose the sequence M. It starts out negative 16, and then it's 4, negative 1, 1/4, and then you all finished it off, and you should have had negative 1/16, and then positive 1/32. So we're going to, again, write the explicit and recursive formula. Let's start with the recursive formula. This time it's geometric, so we need to make it a g instead of an a. So we know that g to the nth term is going to be equal to g to the n minus 1 term, the previous term, times r. And r is just our common ratio. Well, in this case, our common ratio is negative 1/4. We're multiplying everything by negative 1/4 each time. So I'm going to plug that in order to find the fifth term. So g to the 5, which is the geometric fifth term, is the fourth term, g4, times negative 1/4, because that is my ratio, my common ratio. Now, g4, our fourth term, is listed right there. It's 1/4. So really, my fifth term is 1/4 times negative 1/4. We know that a negative times a positive is a negative, and we know that 1 times 1 on the top is 1, and 4 times 4 is 16. So the fifth term here should have been negative 1/16, which is probably what most of you already had as the fifth term. Now we're going to go over to the explicit side and write an explicit formula. It's going to start out very similar. G to the n, gn means the nth term of the geometric sequence. It's going to be equal to the first term in that sequence times r to the n minus 1 power. Now let's go ahead and plug in what we know. if we're trying to find the 18th term, this is G18, 18th term. It's got to be equal to our first term, which is a negative 16, times our ratio, which is negative 1/4, to the n minus 1. Well, 18 is our n, so it's got to be 17 to the 17th power. Now, when we get this, it's going to be a really, 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 really small number. Your calculator is probably going to give you either a whole bunch of zeros after the decimal, or it may even put it into scientific notation. So on this one, the way I'm going to write it is just like this. G to the 18th is going to be equal to negative 16 times negative 1 to the 4 to the 17th power, which we know is a really, really, really small number that we're multiplying 16 by. And our calculators could spit out a decimal. If you want to put the decimal, that's fine. But really what I want to know is just that I can put this formula in. So if you don't come up with an actual answer on some of these that get really, really, really small, that's okay. All right. So there's an example of what you need to do. You can even use these two examples. So you have two done. So your task is to complete the rest of these tables or graphic organizers or whatever you want to call them, where you are matching the graph with the sequence and then writing the recursive and the explicit formula. Okay? Great job. You guys have been working really hard, and I know that you're going to do awesome on this work.